Today we're going to look at the Arrhenius equation, and this relates K, our constant, to something called A, which is the Arrhenius constant, we'll get to that, EA, activation energy, and temperature. So let's go through what all these things mean. To start with, K is your rate constant, what we've been dealing with. A is the Arrhenius constant. This big E with the A subscript is activation energy. Which will be in kilojoules per mole. R is your gas constant, that 8.31. And T is temperature in Kelvin. So left over is this little E. Well, this is Euler's constant. Like in math, when you deal with logarithms and natural logarithms, this is dealing with that. Well, a more viable version of this expression happens when you take the natural log of each side, and so you get the natural log of K equals negative EA, activation energy, over RT plus the natural log of A. And if you graph this, well, let's back up. Do you see how this has the general form y equals mx plus b, where your slope is the negative activation energy over r, and your x is the inverse of your temperature, since it's 1 over T, and then your A, your intercept, is the natural log of A. So we can use this graphically. Alright, let's take a look at example 11. The following data were collected for a reaction. Determine the activation energy for the reaction in kilojoules per mole by a graphical method. So we're given the rate constant, K, and we're given the temperature in Celsius. So we're not gonna graph K, we're gonna graph the natural log of K. So, and we're not going to graph temperature, we're going to graph 1 over temperature in Kelvin. Okay, so we could do old school and plot all this, or we can use our fancy schmancy calculators, right? Okay, so here's what I've got. Let's see if we can get rid of that glare. Okay, so I have, that's natural log of K, and then I just titled it inverse T. And so if you look at what I've plugged in, I've got the natural log of each of the K values. And then over here I've got 1 over whatever temperature was in Celsius plus 273. Okay, so I'm going to add a page, and I'm going to add data and statistics. I'm going to go over here and click on the y-axis, and I want the natural log of K on the y-axis, and on the x-axis I want my inverse of my temperature. And look, we get this line that should be linear. Let me go back a page and look at what I put in. Okay, I'm not quite sure why it's turning out this way, but what we'll do with this is we'll go to Menu, Analyze, and then down to Regression, Linear Regression, And again, I don't know why I'm getting this funky line, because what I should get when I did this earlier was, so I said menu, analyze, linear regression, I got this equation. And this is what I should have gotten. So it should give me a negative slope line. Again, this is natural log of k over 1 over t. Well, what I'm concerned with is this slope. Negative 9515 equals my activation energy over R, which is a gas constant. R is 8.31, so negative 9515 equals EA over 8.31. If I multiply both sides by 8.31, I get my activation energy to be 79,070, and that's joules per mole if we look at all our units associated with this. But to get it in kilojoules per mole, I'm going to say 79.1 kilojoules per mole. So again, you get this equation. Let me show you. It's actually in your data booklet. You get multiple forms of this. So if we look, relevant equations, section 1, here's the first version, and then here's the second version with the natural logs, and it's this second one that you'll use the most frequently. Okay, let's look at some other versions of this expression. Okay. So we can also measure the rate constant at a couple different temperatures and get the ratio of the rate constant, and then solve for our activation energy. So we've got these two temperatures, these two rate constants. We're going to calculate the activation energy. So I'm going to call this temperature 1 and this temperature 2. So, and that's in Celsius. I need it in Kelvin. Actually, never mind. I need my K values first. So 3.52 times 10 to the negative 7 over 3.95 times 10 to the negative 2 equals EA over 8.31, 1 over, now notice it's T2 minus T1. So that's going to be 508 Celsius plus 273 to get it to Celsius, to Kelvin, minus 1 over 283 plus 273 again to get it to Kelvin. Okay, and so we will solve this. I'll give you a minute to practice your math skills. And my activation energy comes out to be 69,782, and this is in just joules per mole. So I can make this 69.8 kilojoules per mole. Okay, and there you go.